Rao Bhim 9.4 PD and NND matrices. Now this section gives you some important results, not very difficult results, but simple results that are quite useful when you want to think about a problem. But unfortunately, this section is very badly affected by Rao Bhim way of presenting. So all the results that are given here are basically consequence of this very simple fact that if A is a real symmetric matrix, then it has a spectral decomposition. I say it's a simple fact, not because that it is a shallow result or very easy to prove result, but we have proved it. And it is one of the most fundamental things that should always be part of your thought process. So this basically says that I can write it as P transpose D P, where P I can take it to be an orthogonal matrix. We have also seen that I can just take it to be any non-singular matrix also. So that was the congruent operation. So from this we can read up lots of interesting things. First of all, when will it be PD? It will be PD if and only if all the diagonal entries of D are strictly positive. So PD if and only if for all I dii strictly positive. It will be NND if and only if all of them are greater than or equal to 0. Similarly, you can write it as negative definite if it is strictly less than 0, and that is absolutely straightforward to see. Now, how do you see this? In order to intuitively feel it, you should think in this way, because I know that in every congruent class, so we talked about that equivalence, every real symmetric matrix is equivalent to some diagonal. So without loss of generality, think of the matrix as a diagonal matrix. Then when is a diagonal matrix positive definite? Clearly when all the diagonal entries are strictly positive, because what is meant by that? Suppose the diagonal entries are 1 and 2. So if now you form x1, x2 and x1, x2, then that will be equal to x1 square plus 2x2 square. These being real variables, so they must be greater than or equal to 0 and strictly positive if xi's are non-zero. So this must be strictly positive if both the xi's are non-zero. Now if I put a negative here, immediately you can create a negative value by putting say x1 equal to 0 and put x2 equal to something non-zero. You can make it negative. So you just look at the signs of these. This will be a negative definite matrix. This is positive definite. Make this equal to 0. It is non-negative definite but not positive definite, because you can put some non-zero stuff in x2 and make x1 0. Then this will be equal to 0. So it is basically connecting it up with this. Now, thinking of spectral decomposition, I might just say that A is positive definite if and only if all the eigenvalues of A are strictly positive, or non-negative definite if and only if all the eigenvalues are greater than or equal to 0. So then I am choosing a special P, I am choosing it an orthogonal matrix. But this is true about any congruence relation, in particular even if P is orthogonal. So we have this theorem, it is a matrix is PD if and only if all its eigenvalues are strictly positive. Of course, we are talking about a real symmetric matrix here. Now, you can similarly have, it will be N and D if all of them are greater than or equal to 0. You can have similarly for negative definite these. You can have indefinite if at least one eigenvalue is strictly positive, one is strictly negative, like that. Now, I cannot quickly see what is the number of this theorem in the book. I could not locate it quickly, so it must be somewhere there. Okay, so that is one type of result. Now here is another type of result based on the same idea. Suppose A happens to be this matrix, P transpose, this is my diagonal matrix, then P. Now you can easily see that this is a positive definite matrix because all these numbers are strictly positive. Remember, I am not saying these are the eigenvalues. That will be the case if P also happens to be orthogonal, but I am merely saying that P is a non-singular matrix. Then all that I can see says that if these are all strictly positive, then A must be PD. Okay, now since these are strictly positive, I can split them up by taking square root. So what I can do is that I can do this. So square root of 1, square root of 2, square root of 3, then again square root of 1, square root of 2, square root of 3, p. I will just quickly remind you that when you multiply two diagonal matrices, the diagonal entries get multiplied up. You can check that quickly, that it always happens. So this thing basically gives you square of square root of 1, that is 1, square of square root of 2, that is 2, like that. Now combine this fellow and give it a name and give this a name. Suppose I call this matrix B, then this has to be B transpose because it is its own transpose. So you can write A as B transpose B. And also notice that this B is a non-singular matrix because it is product of two non-singular matrices. Conversely, if A can be written as B transpose B, where B is a non-singular matrix, you can easily check that such an A must be positive definite. From this, we immediately get theorem 9.4.1 and theorem 9.4.2. Both of them work with real symmetric matrix, and it says A is NND if A can be written as B transpose B for some B, and A is PD if that B can also be chosen to be non-singular. Now, one way we have already checked, if it is non-negative definite, then you can write it in this way, simply by taking square root of the diagonal part. Now, let's do the other way around, that is even simpler, directly from the definition. Suppose I am going to show this, then if A is of this form, in that case, let's just see what happens to X transpose AX. I need to show that this will always be greater than or equal to 0. So I have assumed this condition, so this becomes X transpose B, BX. So if I consider this, call this Y, then this will be Y transpose. So it is nothing but summation yi squared. These are all being real valued variables, has to be greater than or equal to 0. So it shows that this implies that. Now if I am working with this, that non-singularity will also guarantee that if I take x not equal to 0, in that case, if B is non-singular, then y will also be non-zero. If B is non-singular, because a non-singular matrix, if you multiply a non-zero vector with a non-singular matrix, the result must be non-zero. So you are also guaranteed that y is a vector which is non-zero, that is at least one entry is non-zero. In that case, you can say it is strictly positive. So that will show that this will imply that. Now this is a very important result because this will be part of your thought process. Whenever someone says, suppose something is PD, immediately you think of it as some B transpose B, because this structure itself takes care of the PD nature. Now the condition reduces to something much more simpler, namely non-singular. Similarly, if I say A is NND, you immediately think of it as B transpose B without any structure needed for the matrix B. So your problem becomes very easy. The less conditions you have, the easier it gets. So you naturally want to replace conditions by structure. So this condition becomes this structure. So this is a very important theorem. Now Rao Bhim has given a corollary to this, namely inverse of a PD matrix is PD. Now you can think of it as a corollary or just as an independent result. First of all, if A is PD, A must be non-singular because A can be written as some B transpose B, where B is non-singular. So B transpose is non-singular, product of non-singular matrices is again non-singular. So inverse exists. So I will take A inverse, and that is, this comes first, B inverse, and then B transpose inverse. Now it's an interesting fact that you should know from elementary linear algebra, but inverse of B transpose is same as B inverse transpose. That is quite an interesting fact. Inverse of transpose is transpose of inverse. So I am again having the same structure, namely a non-singular matrix times its transpose. So this must again be PT. And of course, because A inverse of inverse is the original thing, you have the reverse implication as well. Now all these results are basically consequences of this fundamental thing. For any real symmetric matrix A, I can write it as P transpose the non-singular P, diagonal D and P. And if the diagonal entries are non-negative, we have non-negative definite matrix, otherwise we have PD matrix. Now, we will go a bit deeper into this in the following way. So here I have got the matrix P transpose, then I have the diagonal matrix D, it's diagonal, followed by the matrix which is P. Now what I shall do is the following. I will take the first few columns. So I take, say, k many columns, k many rows, and I will take correspondingly the k many columns. So whatever this thing is the same thing made vertical. Now if I do the multiplication, what shall I have? I'll have this times the entire matrix times this, and this will give me basically the topmost k by k submatrix. So you understand this carefully. So this is the k by k submatrix. This is obtained by multiplying this with the entire matrix D followed by this matrix here. So if I call this part P1 and this P2, well, put transposes, and this is P1 and this is P2, and this is, say, A11, then I can say A11 is P1 prime D, the entire D times P1. Now this structure again quickly shows that this thing, if I have the diagonal entries of D all non-negative, in that case this again must have that property, namely it must be non-negative. And why is that? Suppose I take some X transpose here and some X, so it is X transpose here and X. So if I consider this as Y and consider then this will become Y prime. So what is it? This is summation dii yi squared. If dii are all non-negative, these are being real valued variables, this has to be greater than or equal to 0, and that shows something quite interesting, namely if your original A is non-negative definite, then you take any such submatrix, just make sure that the submatrix is placed symmetrically around the thing. Do not take a submatrix like this, so it must be symmetrically along the leading diagonal. Then that also must be NND. So the fact that I took the first k, and the first k here doesn't matter, you could have taken the last k and the last k, in which case you will get something like this. You can say the middle and the middle, in which case you will get something like this. You can take some here and here, the corresponding thing here and there, then you will get a submatrix which is scattered all over the place, but you are always symmetric around the leading diagonal. So any such submatrix must again be NND. This immediately leads to theorem 9.4.5, which says principal submatrices of NND matrices must be NND themselves. I will quickly remind you what is meant by principal submatrix. They are just things which are symmetrically placed around the leading diagonal. So it could be this submatrix. So it is not in one place, but it's split up in various things. But whenever you have this entry, you must have that entry. It could be like this, it could be somewhere in between, but just make sure that the diagonal of your submatrix lies on the leading diagonal. Now if you replace this NND by PD, it is not difficult to see the same argument will guarantee that principal submatrices of PD must again be PD. Now I have skipped ahead. I have not discussed some of the intermediate theorems because I want to present them in a coherent way, not like Rao Bhim, which just makes a hash of all the theorems, presenting them in this random order. Well, now we start with our next type of result. Again, we start with A equal to P prime dP. Now we take determinant. So if I take determinant of A, I will get determinant of P transpose times determinant of D times determinant of P. Now remember, these and these are the same, and this is something which is non-zero. So it is going to be some positive number, some strictly positive number. So I will write some positive number times determinant of D, and that is simply product of all your DIIs. So you can see that determinant of A is basically a positive number times the product of all this. So if A is positive definite, this was for general real symmetric matrix. If A is positive definite, then all the DIIs are strictly positive. So determinant of A will also be strictly positive. If it is non-negative definite, in that case determinant of A is greater than or equal to 0, because some of them may be 0. Now if it is a negative definite, you might be tempted to say determinant of A is strictly negative. Well, that is not entirely true, because these numbers are all strictly negative, but when you multiply two negative numbers, you actually get positive. So if it is negative definite, then it will be minus 1 to the power n. That will be the sign. So I will say that determinant of A will be strictly positive if n is even, and n means n by n, and less than 0 if it is odd. So we get something in terms of determinant, but they all come from this result. Now we can continue further with determinants, because we have already seen that submatrices, principal submatrices, are also positive definite or non-negative definite, so we can talk about their determinant also. Here is a quick terminology. If you take a submatrix, then its determinant is called a minor for the whole matrix. And if you take this to be a principal submatrix, then this is also called a principal minor. Now you can easily guess that we are going to get a result like this. If A is NND, then we know all its principal submatrices are also NND. So I can say that its determinant must also be greater than or equal to 0. So I can say all principal minors must be greater than or equal to 0. Remember, these are numbers, so because these are determinant, not matrices anymore. Similarly, if I have PD, I must have all these things strictly positive. And if I have ND, then naturally we'll have that sign will be positive or negative depending on whether the size is even or odd. The book calls these two results, theorem 9.4.8 and 9.4.9. In fact, they go a bit further than this. They claim that the reverse implication is also true. So A is NND if and only if all principal minors are greater than or equal to 0. Similarly, A is positive definite if and only if all the principal minors are strictly positive. Let us see how they make these reverse implications. Well, suppose I am working with the PD thing, the other thing will be similar. So what we do is that we first apply just induction, that's all. So all principal minors are strictly positive. I want to show that it has to be PD. Suppose I have shown that it can be done as long as the order is n minus 1 by n minus 1. For any n minus 1 by n minus 1 matrix, I have proved that this result is true. Principal minor strictly positive means it has to be PD. Now someone gives me an n by n matrix which has all principal minors strictly positive. So in particular, this number must be strictly positive because the number itself is 1 by 1 leading principal minor. So what I do is that I will just apply that congruence operation the way we did. So you subtract a suitable multiple of this row from all these so that you turn all these entries into 0 and perform the congruent column operation. So you get these 0. So instead of working now with A, you have arrived at a matrix which is like QA, Q transpose. Or if you want Q transpose AQ. that is of this form, and this has changed to something. Let me call this thing B. So B is indeed n minus 1 cross n minus 1. I want to apply my induction hypothesis to B. So I have to make sure that B satisfies this condition. All principal minors of B are strictly positive. Now that is pretty straightforward, because the principal minors here, they continue to have the same sign or as the original thing, because you can see all that I have multiplied. If I take the determinant of anything here, I'll basically multiply this with the square of the determinant of Q, which is a strictly positive number. So just just here you all that you have to do is to think a little bit and see that the principal submatrices, the principal minors of B are basically principal minors of A multiplied with this little entry. So our induction hypothesis applies on B. All the principal minors are strictly positive. Think about this step a little. So immediately I see that B must be PD, because for n minus 1 by n minus 1 we have assumed that the result is true. So this matrix is of this form, a strictly positive number followed by a PD matrix. So this must be a PD matrix itself. So Q transpose AQ is PD, then A must be PD, because PD is the property that is preserved by congruence, and that proves this way. Of course, this is very similar. Okay, so this video is already quite long. We have a few results still left, but we have covered the main things, and these are very important because you have to work with these things when you solve other problems. So these must be part of your thought process. They are the tools that you can use to solve other problems. So they are not just some fancy theorem.